What if I told you there was a substance on Earth that made cell phones better, renewable energy technology more efficient, and national defense systems stronger? This substance has properties unlike any other, is extremely valuable, but extremely hard to come by. Sounds like something out of a comic book, like vibranium or adamantium. Now, what if I told you that there was only one producer who had near complete control over its market? This would heighten the importance of having a self-reliant, steady supply of this substance. What I am alluding to is not fictional, and it is not one substance, but a family of elements that can be found on the periodic table. The periodic table of the elements, as seen in every science textbook ever, is a collection and, more importantly, a rational organization of the 118 known elements that constitute everything we can observe in the universe. The very act of creating this figure, recognizing patterns in the properties of elements and grouping them accordingly, represents humans' ever-growing understanding of the world around us. It is this growing understanding of these elements that has led and continues to lead to many technological developments. All 118 of these elements shown are unique, useful, and important in some way, but some of the most important elements in this table might elude your eye because they are mostly relegated to the basement. The elements highlighted here represent the family of 17 elements, the lanthanides, yttrium, and scandium, collectively known as the rare earth elements. Their strange names, like ytterbium and lutetium, might sound foreign to you, but their utility should not be underestimated. As I proceed, I will be treating these elements as a group for the most part, talking about them together, but remember that each individual element is unique, special, and important in its own way. I will be referring to the names of these elements, not to confuse you, but to get you used to hearing their names so that they become no longer so foreign in your minds. Rare earth elements are everywhere. They are important in our electronics. Our cell phones function well because they contain 9 of the 17 rare earth elements, all packed into a device that can fit in the palm of our hand. They help optimize the functions of the circuit board electronics, vibrator, color screen, glass polishing, and speaker. A lot of renewable energy technologies use rare earth elements. They help in the function of electric motors that power wind turbine generators and electric cars. They have medical applications. If you have ever taken an MRI, you have come into contact with gadolinium. It is present in both the large magnets of the machine and in your body once it is administered as a contrast agent. Rare earths are also important for future technology, such as the development of quantum computers and nuclear batteries, where one of the rarest elements in the world, promethium, has found use. Rare earth elements are a prime driver of technological improvement. So what makes them so useful in these applications? What makes them special, in part, is their unique magnetic properties. They make for strong magnets, and magnets are extremely important in our technology. Praseodymium, neodymium, terbium, and dysprosium are prime components of magnets. Additionally, europium, yttrium, erbium, and praseodymium have optical properties that make them tailor-made for lighting applications, such as your cell phones. Lanthanum, cerium, and neodymium are used as catalysts. Neodymium and yttrium are used in lasers. Rare earth elements are specialty metals in that they are generally used in small amounts to enhance the performance of high-end technology. In other words, we might be able to get by not using rare earth elements in some products, but they will not function nearly as well. Their current applications are so ubiquitous and their need is only projected to grow. Their supply, however, is critical. This stems from the challenge of their separation from each other. Because, you see, they are referred to as rare earths, not because they are scarce in quantity in the Earth's crust, but rather because they are scarce in concentration and purity. Unlike the rarer element, gold, that forms concentrated veins in Earth's crust, rare earths are most often found together with other rare earths in not so concentrated deposits. It is necessary to separate these elements for their utilization in the technology I previously mentioned. This is no trivial task because, counterintuitive to their wide-ranging applications as individual elements, the chemistry across the entire series of rare earth elements is very similar. A separation is based on exploiting differences in the properties of elements to effect some change that allows the selective collection of one element. As the classic school laboratory example, A mixture of sand, salt, and iron filings can be separated by first holding a magnet up to the mixture to selectively collect the iron, exploiting its magnetic properties. Then you can add water to the sand and salt mixture left behind and filter to collect solid sand and a salt solution, exploiting sands and salts' different solubility properties. And exploitation is extremely difficult when the chemical properties of the elements in question are so alike. The current industrial system for rare earths, based on tiny differences in size, is not very efficient and requires many iterations of the same procedure to achieve pure material. This lack of efficiency leads to high energy consumption and high waste accumulation. These in turn cause the process to not be very economically worthwhile or environmentally friendly. It is for this reason that the United States and most of the rest of the world buy rare earth elements from China. It is cheaper to purchase from China than perform the separation ourselves. China supplies more than 90% of the world's rare earth elements because they have relaxed environmental regulations that allow them to handle the amounts of toxic waste produced and cheap labor to make the inherently inefficient process economically worthwhile. This monopoly on rare earths held by China puts other countries at their mercy, considering the high demand for these elements in important technology. The world has a demand, and China has most of the supply. The world's rare earth economy would greatly benefit from having competitors with China, but competitors need better separation processes. How do we do this? With chemistry and the periodic table. We need more efficient, environmentally friendly, cost-effective methods of separating rare earth elements. The United States has the means. We have access to rare earth minerals, but we need the right method. A new and improved separation process requires creative thinking. It requires the creative exploitation of differences in the properties of the oh-so-similar rare earths. The development and tailoring of such a separation system requires creativity and, most importantly, a fundamental understanding of the chemical properties of these elements. And it is with this that I go back to one of the first figures I presented, the periodic table of the elements, the representation of our understanding of the building blocks of the world around us. Knowledge of this table and its constituents, especially the rare earth elements, is important for the future of our technological development. I hope I have shown you why this highlighted, often neglected section of the periodic table, the rare earth elements, are extremely important in our present and for our future, and I hope you now understand why I and other chemists are trying so hard to find effective ways to separate them. Thank you so much for your time.